We've already learned how to multiply matrices together. In this video, we'll take a look at what does it mean to take an n by 1 vector and multiply it by a 1 by n vector. But before we do that, let's recall that when we multiply two matrices, and I'm going to go ahead and pick a 2 by 3 matrix with a 3 by 2 matrix. We know that the result that we get, because the inner dimensions match, we're going to end up with a 2 by 2 matrix. And let's place some values in here. 1, 2, 3, 4, 5, 6, and maybe we'll do 1, 0, 2, 0, 3, 1. Now the way matrix multiplication takes place, the way we've described it, is that every column in the first matrix gets scaled by the corresponding component in, first of all, the first column, and then we add up those two vectors. So we're taking a linear combination of these three vectors in the first matrix. And the way this pans out is that we take 1 and we multiply it by the first vector, 1 times the 1, 4 vector. We add to that 0 times the second vector. And we add to that 2 times the third vector. Now, since we're done with the first column of the second matrix, we are now going to move to the next column of the second matrix, which produces a new column in our final product matrix. So now we're going to repeat the same thing, but we're going to do it with the components 0, 3, 1. And once again, those will scale the same respective components as the first vector in the second matrix. So here we'll have 0 times the 1, 4 vector plus 3 times the 2, 5 vector plus 1 times the 3, 6 vector. Now, all that's left to do is to reduce these. 1 times 1 plus 0 times 2 plus 2 times 3 will give me 7. So that's going to be the top component of this first linear combination. And then I'll have 1 times 4 plus 0 times 5 plus 2 times 6. That's going to give me 16. And so that really is what this vector linear combination here produces. Now I don't need to put it in vector form anymore. The only reason we wrote it like this is to show how the arithmetic is going to take place. Now I'll repeat the same thing for this set here. 0 times 1 plus 3 times 2 plus 1 times 3 will give me a combination of 9. 0 times 4 plus 3 times 5 plus 1 times 6 will give me a linear combination value of 21. And so there is our final 2 by 2 matrix. Now, at first it may seem a little deceptive when we're working with an n by 1 and a 1 by n matrix, but if I take a look at an n by 1 multiplied with a 1 by n, since the inner dimensions match, I should end up with an n by n matrix. So here we took a column vector. The reason I'm calling this a column vector is because it's a single column of values, and this here is a row vector because it is a row, a single row of values, and what I end up with is an n by n matrix. An n by n matrix. Now, vectors are matrices in their own right. Vectors are matrices, but not all matrices are vectors. Matrices do not necessarily have to have one row or one column. So this is going to be an n by n matrix. So here we have n rows, and we have one column. Here we have one row, and we have n columns. And here we're going to have n rows, and we'll have n columns. So how does that pan out? Well, let's take a look. So let's say that we have a column vector that just contains the elements 1, 2, and 3. And then I have a row vector which will contain the elements 1, 0, 4. how do we carry out this multiplication? And how do we end up with an n by n matrix? Well, the dimensions tell us. But when we think about this process, we have to think about it in very much the same way as we did when we had matrices that were not vectors. So how did we start? We said that all of the columns in the first matrix, well, there's only one of them, gets multiplied by the first column of the second matrix. So this is the first column of the second matrix. Now there's only one element there, but that one element will multiply or still scale that single column that we have in our first matrix. So what's going to happen here is that 1 is essentially just going to scale the 1, 2, 3, 1 times 1, 2, 3. But since I do not have any additional columns in the first matrix, and since I do not have any additional rows in the second matrix, there's not going to be anything to add to this. There's nothing to add. If we take a look back over here we had 3 columns and 3 rows. Each column in the first matrix would get scaled by each of the rows in the second matrix. And in our case, we only have 1 column in the first matrix and 1 row in the second matrix. Therefore, this element is just going to have a scaling effect on our output here. Now we're going to repeat that because now we're going to move to the second column. So this second column is again going to act as the scalar for all columns of the first matrix, for which there's only 1. So that will be 0 times 1, 2, 3. And now in this case, I have to move on to the third column of the second matrix. The third column just consists of 1 element, which is 4. And again, that will scale the single column of the first matrix, which will be 4 times 1, 2, 3. And there we go. So there's no summation taking place here because it's just 1 column scaled by 1 row element in the second matrix. And so what I'll end up with is the vector 1, 2, 3 in the first column, the vector 0, 0, 0 in the second column, and the vector 4, 8, and 12 in the third column. So we started off with a 3 by 1 vector multiplying a 1 by 3 vector and ended up with a 3 by 3 matrix.